Hello again. In this video, we're going to go over section 2.7, which is about a more precise definition of the limit of a function. And it's known as the epsilon delta definition of the limit of a function. Okay, so here's what the definition says. Assume that f of x is defined for all x in some open interval containing a, except possibly at a. We say that the limit of f of x as x approaches a is equal to L if for any number epsilon greater than 0, there is a corresponding number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. Okay, so there's a lot to take in here. I think the first thing we should talk about is how we're going to interpret these absolute value inequalities. So let's talk about that first. So this absolute value of f of x minus L being less than epsilon can be interpreted in various ways, which we talked about in the previous video. Remember, L is the center, and then epsilon would be the tolerance. And so you can think of this as L plus or minus epsilon, and that would be the tolerance for f of x. So f of x is trapped between L plus epsilon and L minus epsilon. Okay, that's what this inequality is telling us. Now in terms of distance, the distance between f of x and L is less than epsilon. That's another interpretation of this inequality. Now for this one, which is the other absolute value inequality that we have in the definition, in this case a is the center and delta is the tolerance. So it's a plus or minus delta, so x is trapped between a plus delta and a minus delta. That's what this is kind of saying. And in terms of distance, you can interpret it as the distance between x and a is less than delta. Okay, so let's go back to the definition and keep these interpretations in mind. Okay, so what do we mean? What's the definition of the limit of f of x as x approaches a equaling to L? What do we mean by that? We mean for any number epsilon greater than 0, there's a corresponding number delta greater than 0, such that the distance between f and L is less than epsilon whenever the distance between x and a is less than delta. I think that's the best interpretation of these inequalities. Okay, so having said that, I'm going to look at an example here to kind of show you how this definition works. Okay, so let's look at example 1 here. So here's the graph of some function. Notice it has a hole in it right when x is equal to 3. And let's say we want to find the limit of this function as x approaches 3. And I think you can see as you approach 3 from the right-hand side, the y value is getting closer to 5. And if you approach 3 from the left-hand side, it's also getting closer to 5. So the two-sided limit would also be 5. So we know this limit's equal to 5, right, as x gets closer to 3. But let's look at the formal definition, the epsilon delta definition of the limit. Under the epsilon delta definition of the limit, for any epsilon greater than 0, we must find a corresponding delta greater than 0 such that the distance between f of x and 5, which is L in this case, is less than epsilon whenever the distance between x and 3, okay, a is 3 in this case. Okay, notice x is approaching 3. Whenever the distance between x and 3 is less than delta. Okay, so in this case, the L is the 5 and the a is the 3. So this is f of x minus L, so f of x minus 5. and then the absolute value of that must be less than epsilon whenever the distance between x and 3, okay, x is approaching a, in this case a is 3, whenever the distance between x and 3 is less than delta. Okay, so here's what we're going to do. Let's just play with this. I've got to do this for any epsilon greater than 0. So let's just pick some epsilon greater than 0, and we have to find a corresponding delta which would satisfy this statement. So let's pick epsilon to be greater than 0. Now, we're going to try to find a delta that's greater than 0 that satisfies this statement. Let's see if we can't find it. All right, if epsilon is equal to 1, okay, so let's go and write this down. So this is for epsilon equal to 1. Okay, we want the distance between f and 5 to be less than epsilon, and we're picking epsilon to be 1, whenever the distance between x and 3 is less than some delta. All right, so if we pick epsilon to be 1 over here, okay, remember 5 is the center and 1 is the tolerance. So we're talking about 5 plus or minus 1 here. And so that tells us that f of x must be trapped between 5 plus 1 and 5 minus 1, right? So f of x would have to be between 4 and 6. Okay? We've got to show that this happens whenever the distance between x and 3 is less than some delta, and we have to find that delta. Okay? Well, let's interpret this. Let's see, this means 3 is the center, and this is the tolerance delta. So 3 plus or minus delta. So in other words, x has to be between 3 plus delta and 3 minus delta. Okay? So we've got to show that f of x is trapped between 4 and 6 whenever x is trapped between 3 plus or minus some delta. All right, let's see if we can't find that delta. I'm going to go back to the graph and see. So we're going to look at f of x and see when it's trapped between 4 and 6, and then try to figure out what x would have to be trapped between, and then try to figure out what delta is from that. Okay, I'm going to go back to the graph to do this. Okay, so we want f of x to be between 4 and 6. Okay, so if f of x is going to be between 4 and 6, right, which is in here, then that would mean at 4, x would be 1, right? When x is 1, that's when we get a y value of 4. And if the y value were 6, that would mean x is 5. So isn't f of x trapped between 4 and 6 whenever x is trapped between 1 and 5, right? Okay, so let's go back. I need x to be trapped between 1 and 5, right, in order for this to happen. In order for f of x to be trapped between 4 and 6. Okay? And so what does that tell me about delta? Well, delta, it looks like delta needs to be equal to 2. Okay? Because if delta were 2, right, this implies delta must be 2, because if I say 3 plus or minus 2, that's going to give me this range, right, of 1 to 5. So it looks like delta needs to be 2. So I'm going to go back up here and plug in 2 for delta. If delta were equal to 2, then yes, x would be between 1 and 5. Okay, so let's see if this makes sense. If I pick epsilon to be 1, I need to find the corresponding delta that would make this statement true. And I'm going to claim that delta would have to be equal to. And so let's see if that's true. If epsilon is equal to 1 here, then that means f of x would have to be between 4 and 6 whenever x is trapped between 1 and 5. And that's true, right? If you go back and look at the graph, f of x is trapped between 4 and 6 whenever x is trapped between 1 and 5, right? Okay, now that's only if someone happens to pick epsilon equal to 1, right? We have to show that this is true for any epsilon, so any positive epsilon. Okay, so for each value of epsilon greater than 0, we have to find a corresponding delta that's greater than 0, which would satisfy this statement. Okay, so let's keep doing this just to get practice. Let's try it for epsilon equal to a half. Okay, if epsilon were 1/2, let's try to find the corresponding delta that would make this statement true. All right, so I'm going to go back to here, and let's change this epsilon to 1/2. Okay, so that means 5 is at the center, and I have a tolerance of a half. Okay, so we're talking about f of x being trapped between 5.5 and 4.5. Okay, 5 plus 0.5 and 5 minus 0.5. Okay, so let's write that down. That's 4.5 to 5.5. Now, for this epsilon, I have to find the corresponding delta over here. Okay, so let's see if we can't find it. Okay, so I'm going to go back to the graph to try to figure that out. Okay, so now we want f of x to be trapped between 4.5, which is right there, and 5.5. Okay, so for which x values is this true? Let's see. For 4.5, it looks like x would have to be 2. And at 5.5, the x value looks to be 4. So if x is between 2 and 4, it looks like f of x would be trapped between 4.5 and 5.5. Okay, so 2 to 4, okay, that has a center of 3 with a tolerance of 1. So 3 plus or minus 1, right? If you write it in those terms. So we're talking about 3 plus or minus 1, right? So that means delta has to be 1. If you want this to be 3 plus or minus 1, that means delta would have to be 1. Okay? So let's put that back in here. In other words, 3 plus 1 would be 4, 3 minus 1 would be 2. Okay? And that corresponds to x being between 2 and 4. So this means delta would have to be 1, right? Okay, so if you say epsilon is equal to a half, then my corresponding delta would be 1. That would make this statement true. Okay, so this is just an example trying to give you an idea of how this definition works. You could continue to do this and continue to pick like epsilon equal to 1/4 and then try to find the corresponding delta that would make this statement true. But in the definition, you must show that for any epsilon greater than 0, that there is a corresponding delta greater than 0 that would satisfy this statement. And so this is not really a proof. A proof would show that no matter what epsilon I pick that's positive, I can find a corresponding delta that's positive to make this statement true. Okay? And in the next video, I'm going to show you how to prove that this limit as f of x of f of x as x approaches 3 is equal to 5, I'm going to show you that this is true using the epsilon delta proof for any epsilon greater than 0, not just for specific ones like we're doing here. And that would constitute a formal proof of a limit, showing that a limit of f of x as x approaches 3 is equal to 5 in this case. Okay, so I'm going to do that in the next video. Okay, I hope this video was helpful. Thank you for watching. Bye-bye.